Hi, hello, and welcome to the Physics Clinic. Now I'm going to discuss about solenoid. Okay, so it's a kind of a bar magnet. Its properties and everything it resembles bar magnet. Okay, by long solenoid, we mean that the solenoid's length is large, very much large when compared to its radius. That means let imagine like it is a cylindrical tube. Okay, so it's a cylindrical tube or something. It's a metal tube, and then there the coil of wire is wounded. Okay, from one end of the tube to the cylindrical tube to the other end of the cylindrical tube. Based on the number of turns of the coil, the current is flowing through the coil. Thereby, we can learn about what about the magnetic field induced in it. Magnetic field, we can learn its direction, okay, how it moves. So, what is the procedures and where the charges will be, everything we are going to learn from here, okay, about the solenoid, okay. It's a kind of construction part. It consists of a long wire wound in the form of a helix. So we saw, right? So like a helix. Helix mean it will not complete the round, like a twine in a cylindrical cord, right? So it is actually helical wounding of a wire. Okay. It consists where the neighboring turns are closely spaced. There is no space in between. Like you can imagine a twine in a rod. Okay, that cardboard cylindrical shape. It is wounded, right? So like a way. So each turn can be regarded as a circular loop. So we have discussed about the helical loop in earlier. So the same we have to consider here. So, sorry, the net magnetic field is the so each and every turn has its own magnetic field. So totally the net magnetic field is all the vector sum of the fields due to all the turns. So enameled wires are used. What is that? Insulated from each other. From one wire, it doesn't touch with the other wounding. Okay, other helical shape. Okay, so that should be closely spaced as well as it should be insulated. Okay, then. So this picture clearly shows that the magnetic field due to a section of the solenoid which has been stretched out for clarity. So it's an exaggerated one. Okay. So what it is given, only the exterior semicircular part is shown. Notice how the circular loops between neighboring turns tend to cancel. That means, what is that first part? The magnetic field due to a section of a solenoid. Okay. So it is a section of a solenoid, this one. Okay. Only the exterior semicircular part is shown. So this is exterior semicircular part. So like this, it is shown. Okay. So how the circular loops between neighboring turns tend to cancel. So that and all it is given. So some fields are letting inside and some fields are outside, right? These two cancel together. Inwards and outwards. Same number of fields inwards and same number of fields outwards. It cancels. Okay. Then the magnetic field of a finite solenoid, second one. This is finite solenoid. This is just they are showing, they are exaggerating this part. Okay. So now I will explain about this figure 4.15. Okay, field lines of a finite solenoid, we can take it in a account. We show a section of the solenoid in an enlarged manner in 4.15a and 4.15b shows the entire finite solenoid with its magnetic field. Okay. So in this figure, it is clear from the circular loops that the field between two neighboring turns vanishes. That and all we saw. One is inside, one is outside. So it vanishes. In B, we show that the interior midpoint P is uniform, strong along the axis. That is the major difference. Okay. Strong along the, here it is densely populated all the magnetic field lines. So here we can see at the center, we can see the field between field at the interior midpoint is uniform, strong. Okay, it is densely populated and along the axis of the solenoid. Understood? So, this is the axis of the solenoid. So, it will be along the axis of the solenoid like this. Then, what else it is given? The field at the exterior midpoint Q is V. Okay, and moreover, it is along the axis of the solenoid with no perpendicular or normal component. Okay, here, no components here. So, as the so here this section 4.16 it shows the magnetic field of a very long solenoid. We consider so here it is a short solenoid. Okay, very finite solenoid. This is very long solenoid. Okay. Um, we consider rectangular Amperian loop ABCD. See here. This loop we are considering. Amperian loop means in this the current is flowing. Okay, magnetic field is like uniform in this cross section. We are just exaggerating here. Okay, so here it is inside and outside. So cancels together, the field is cancelled together. Then current is flowing. You are considering this loop alone, like Gaussian surface. Here, Amperian loop. It is resemble to the first lesson, Gaussian surface. It resembles, okay, to determine the field. There also we use Gaussian surface to determine the electric field. Here we are using Amperian loop to determine the magnetic field, okay. So the solenoid is made longer, it appears like a long cylindrical metal sheet. I've told you, no? So everything it is given. The field outside the solenoid approaches zero. The field outside is approaching zero, right? There is no charges there. So field outside is zero. The field inside becomes everywhere parallel to the axis. See here, it is the axis, so it is parallel to the axis. Field inside. So consider rectangular Amperian loop ABCD. Along CD, the field is zero because it is in line. It is perpendicular. CD is perpendicular to this magnetic field. 90 degree, if you put 90 degree, cos 90 will be zero, right? That we have discussed in earlier. So cos 90 will be zero. So field is zero there along CD. So along transverse sections BC and AD, the field component is zero. So here BC, one second. So, as per our rule and argument, this BC and AD are perpendicular to the field. So, it is the magnetic field along this will be zero. Okay. So, the field is zero. That's how these two sections make no contribution. So, let the field along the AB to B. So, here. Okay. This is AB. AB to B is along the field, right? So, and then the relevant length of the Amperian loop is L we are taking, that is H. This L is we consider as H. Okay. Then, so what it is given, let N be the number of turns per unit length, then the total number of turns is N into H, right? Okay, if N number of turns per unit length is we are taking, then we are considering the total number of turns is N into H. The enclosed current we are talking about. What is the enclosed current? Okay, what is it actually? The enclosed current will be IE, I suffix E it is given. So for all N number of turns, it will be N into H. So I into N into H, where I is the current in the solenoid, okay? From the Ampere circuit law, you know the formula B dot dl. So in Gaussian surface, using Gaussian law, you can find E dot dl or E dot ds, like surface. You consider like a surface that is equal to Q by epsilon naught. But here we are not considering charges, we are considering only current because electron is highly responsive. Electron is the one which is responsible for producing magnetic field, the spin of an electron. Okay. The electron, free electrons are responsible So free electrons produces current only. Here in the first two lessons, we have considered both positively charged ion, that is positively charged, and negative charge also. So positive charge and negative charges are considered in the first two lessons, that is the electrostatic charges. So here we talk about after current electricity. I've explained already about the current electricity. Then in that current electricity, which is responsible, current, the free electrons are responsible, which is moving with drift velocity. That electrons are responsible for magnetic field also. So we are considering only here current. So instead of this, it will be B dot L, BL. B into L, that is equal to 1 by epsilon naught, can be considered here as mu naught. So this is the permeability of a free space. And then what is this? IE. IE is the enclosed current overall in the loop. So IE is equal to I into N into H. So that is, so you have to substitute. So what is the resultant? H gets cancelled. So B is equal to mu naught into N into I. So the direction of the field is given by the right hand rule. You know that right hand rule already we saw. Okay. So solenoid is commonly used to obtain uniform magnetic field. We shall see in the next chapter that a large field is produced by inserting a soft ion core inside the solenoid. That and all we are going to see in the next lesson. So the field also, you know, right? What thumb represents, what is the curl of the finger represents, everything you know about the right hand rule, right? So then uh, this problem is very easy. Directly it is given. You can go through it. Then I will explain you about the force between two parallel currents. So here we are talking about parallel currents. That means two individual wire or something where the free electrons are. So if there is any flow of free electrons, definitely there is a current. So we are considering two current elements here. Currents, two currents, IA and IB. It kept in a parallel condition. So the thing separated by this will be D. Like we saw in the second chapter, that is the parallel sheet, right? Thin parallel plate, which is separated by a small distance. What it is actually? Any guess? Capacitor, right? So, like a way you can imagine. And then here you are considering Amperian circuit. So, let me explain you. Magnetic field due to a conductor carrying a current which obeys the Biot-Savart law. So let me read from your book each and every point from your book. I will tell you actually this textbook is given by the NCRT people. They they just give you a solid foundation. Okay. So all these points are a summary which should be elaborated, which should be learn extras. Okay. That is from the reference books that is prescribed by the NCRT. So we are having materials also, so which is very useful for your reference book. Uh, the exam will be conducted, whether it is competitive exams or board exams. The exams will be conducted in such a manner that 50% from your textbook, 50% from the reference book, both are given by NCRT people. So this is the CBSE board actually exam kind of thing. So when you want to write, if you want to write all the competitive exams, that also you need to consider uh, reference books. There are a lot of reference books suggested by NCRT people. You can't find such a time to get into this. Okay, so we are providing a very good material which will be more helpful. Okay, for your exams. So later on, I will add few problems from that book also. So do follow us so that you will be getting our videos in a frequent manner. Okay, so you can post your doubts also in the comment sections if you're having. Okay, so then I will explain you about this thing. So always keep in your mind what is the magnetic field. So there is an analogy between the electric field and the magnetic field because electrons are responsible, right? So in such a way, first two lessons deals with the static charges. Third one deals with the flow of electrons. So here we are considering the current flowing through the conductor. So that is responsible for the magnetic field. So this electric field and the magnetic field perpendicular to each other. And then we know that there is a movement, right? There is some velocity involved in that. So that represents the magnetic Lorentz force, right? B cross V. Q into B cross V is the magnetic Lorentz force. So you have to take an analogy between magnetic field and the electric field, which is expressed in first lesson. Okay. So this will help you more to get revised more and more. Okay. So further we learn that, so that I'm just reading each and every point in your book. Okay. So generally the children are allowed to close your book, okay, while taking classes, but I'm different. I want to give you a revision kind of lessons. Okay. See, when you open a book, you must know about all the points, the meaning of all the points. Okay. So that it won't be a strange for you, all the concepts which is given in your book. Unless otherwise, nowadays the children are uh, very poor in grasping all these things when compared to other your interesting areas. Okay, you'll be very interesting in gamings or something which is more interesting to you. But when education side it comes, you're showing less interest. So you're not grasping fully from your classrooms. So this is how I'm just helping you to know more about your book. Okay, so this follows from the Lorentz force formula. Just now I've explained. It is logical to expect that two current carrying conductors placed near each other will exert magnetic forces on each other. Okay, this and all we know. Two current carrying conductors placed near each other means it will exert magnetic forces on each other. So it will be overlapped. In 1820 to 25, Ampere studied the nature of this magnetic force. So 1820 to 25, they are very genius. And then, so my kind of coaching is actually I mean, you can be in a scientist perspective. Okay. So your thinking should be like scientist perspective so that it will be given you a clear level of understanding of all the concepts which you can apply for problem solving, any kind of problem solving. Okay. So then Ampere studied the nature of this magnetic force and its dependence on the magnetic magnitude of the current. Okay. On the shape and size of the conductors as well as the distances between the conductors. Okay. What is that? What it depends upon the magnetic force, the nature of the magnetic force, and its dependence on the magnitude of the current on the shape and size of the conductors as well as. Okay, as well as the distance between the conductors also. So what is the meaning of that? So Ampere studied the nature of this magnetic force, okay, and its dependence also. How it is depending the magnitude of the current on the shape and size of the conductors as well as the distance between the conductors. These three keep in your mind. What is that? The magnetic force and its dependence on the magnitude of the current. How much current is flowing on. So that on the shape and size of the conductors as well as the distances between the conductors. Everything matters. So in this section, we shall take the simple example of two parallel. So this is very simple. From this, you can get a very good idea. So like a way, in your book, you are given one simple example. Out of it, there are a lot of scenarios or cases built based on this. So when you understand this concept clearly, then that any cases what you are all given in your question banks or question papers, or if you are given any case based type in your JEE or NEET, whatever it might be. So any kind of competitive exams, it will be helpful when you clearly understand this basic example. So this can be developed for its, I mean, what I'm trying to say, any kind of cases. Okay. So which will perhaps helps us to appreciate Ampere's painstaking work. Okay, really it is very important. So you just see the picture, it will perhaps helps us to appreciate. So that means we can appreciate this Ampere's work, right? So what did he do? Unless otherwise we are not enjoying all these magnetic fields, right? So This is actually A and B are the two conductors, and then you saw here. So this is the consider surface, like a Amperian surface. Then the force is also here. The force is always perpendicular to the uh, conductor, and then I will explain you. This force and the motion of the conductor is we have seen in the first class, right? So B and V should be along the plane, and the force is perpendicular to V. So like a wave only here, it doesn't violate any laws, what we have seen already. So, okay, this thing is given here. What is the magnitude of a magnetic field? BA. So BA had an influence of the current which is passing through that particular coil. So mu naught IA by 2 pi D. What it is, this L stands for 2 pi into D. Okay. Since it is the wire is a cylindrical nature, the wire is in cylindrical nature, and then the cross-sectional area is circle, right? So around the circle, around the surface of a circle, it will be 2 pi D. Okay, that is the circumference of a circle. Similarly, the conductor B carrying a current IB, so that also it will experience a sideways force due to the field BA. It will experience, first you are considering this field BA, and the second conductor will experience the force BA, sorry, the field BA sideways. Okay, so the direction of this force is towards the conductor A. Okay, so and then we label this force as FBA, the force on a segment L of B due to A. So this force is magnetic forces FBA, which is the force due to A on B. Okay, so FBA is equal to IBL into B. We can take like that. Okay. So what is this? If you substitute all these values, then you'll be getting FB is equal to mu naught IAIB by 2 pi D into L. Okay. So you know that these two considerations F, A, B. So similarly, there is a in turn again a force, right? A to B and then B to A. So these two are equal and opposite. There is an influence on B by A. Again, there is an influence on A by B. So both are following consistent with Newton's third law. So at least parallel conductors and steady currents, we have shown that Biot-Savart law and the Lorentz force results in accordance with Newton's third law. It doesn't obey, it doesn't deviate from the law. So we can take when we have time independent currents or charges in motion, Newton's third law may not hold for forces between charges or conductors. Okay, an essential consequence of the Newton's third law in the mechanics is the conservation of momentum of an isolated system. So this is not an isolated system. So this, however, holds even for the case of time-dependent situation with electromagnetic fields. Okay, which provided the momentum carried by fields is also taken into account. What is the meaning? So this Newton's third law may not hold for forces between charges or conductors. Okay, but here what it is satisfying. So how we can say FBA is equal to minus FAB? Whether we can say this? Okay, so these two forces are, I mean, may not hold Newton's third law. Since there is an essential consequence of Newton's third law in mechanics. What is that? Conservation of momentum of an isolated system. So that means there is no loss. No loss should find in this. Okay, the force shared in between the two parallel conductors should not be lost in such a way. But we don't know about that, right? So, however, maybe it might be like that. It stands for the conservation of momentum or may not be. So this, however, holds even for the case of time-dependent situations. So time-dependent currents means if you are considering that particular time period, what is the time period? Whenever the conduction takes place. Okay, so that is the time period. If we stick on to the time period, that is electromagnetic fields. Whenever the magnetic material is kept in a electric field. Okay, then it becomes magnet. So for this kind of electromagnetic fields, it provided the momentum. That means it needs input, right? It needs input means electric field is needed. So that input is now converted into magnetic field output. So if there is no loss in this conversion, then we come to the conclusion it preserves or it holds the law of conservation of momentum, which obeys Newton's law, Newton's third law. Understood? So this part is very important, clear about all these things. So this kind of discussion is given in your book. So parallel currents always attract, anti-parallel currents repel. Like this also you can take it from this part. So like you're not considering the forces, so you are considering the currents. If it is parallel currents, it will attract. Using this, definitely you'll be asked so many questions out of it. In the upcoming classes, I will discuss about the questions which is relevant to this parallel current and anti-parallel current. Okay, keep in your mind. So this rule is the opposite of what we find in electrostatics. That is also very important. Okay, anti-parallel currents repel, not parallel currents. Only parallel currents attract. But in the previous one, opposite charges only attract. Okay, here parallel currents only attract. So this is something different. Okay, that is explained here. So FBA represents the magnitude of the force capital FBA per unit length. Okay, if you consider for unit length, cut L alone from this per unit length. So FBA divided by L will be mu naught IA IB by 2 pi D. What is this actually? It is small FBA. Okay, see, in your book it is given in order to define, in order to designate that. Okay, so ampere is the value of that steady current which maintained in each of the two very long straight parallel conductors of negligible cross section. So the cross section will be very negligible. Okay, placed on 1 meter apart in vacuum. That means it talks about the wire. Okay, so the conductor means wire. The wire must be very thin. That is what they are telling. Okay, so and placed 1 meter apart in vacuum. So you must imagine lot of things. When you are given some statement in your book, don't mean it literally. You had to think. Okay, so it flows, the value of that steady current which maintained in each of the two very long, straight, parallel conductors of negligible cross section means the wire will be thin. Thin wire. Okay, it placed 1 meter apart in vacuum would produce on each of these conductors a force equal to 2 into 10 power minus 7 newtons per meter of length. Keep this in your mind. Okay. Out of that, we can calculate this. Okay.